When the intense summer heat finally peaks, it is often very tempting to view home cooling as a simple financial ladder. The logic seems straightforward. If the budget is tight, you buy a fan. If you have a bit more to spend, you upgrade to an air cooler. And if you have the money, you buy an air conditioner. But treating these machines as a sequence of good, better, and best is a mistake. They operate on entirely different mechanical principles and respond differently to the environment around them. This graph tracks the relationship between upfront purchase price on the horizontal axis and the monthly electricity bill on the vertical axis. While a fan and cooler stay relatively low on both, the air conditioner represents a massive monthly financial liability. However, the effectiveness of that spending depends almost entirely on local ambient humidity. Choosing the right cooling system requires mapping the technology you buy directly to the specific climate data of your city. The ceiling fan relies on a simple, low-wattage motor to circulate the existing air inside a room. It does absolutely zero to lower the actual temperature of the space. Instead, moving air accelerates the evaporation of moisture on your skin, drawing heat away from your body. Because they lack a compressor, fans cost very little to operate. But once the ambient room temperature pushes past normal human body temperature, pushing hot air around ceases to provide physical relief. An evaporative air cooler takes a different approach. It uses a fan to pull hot, dry ambient air through water-soaked cooling pads. As the water evaporates into the passing air, it absorbs heat. The air exiting the machine is physically colder, and the entire process uses a fraction of the electricity required by a traditional compressor. This split-screen simulation shows evaporation in different environments. On the left, in a dry climate, water easily evaporates, but on the right, saturated air blocks cooling. If run in a humid city, the room rapidly transforms into a damp, sticky space. To keep the system running effectively, the homeowner must constantly refill the water reservoir and leave windows open to ensure strict cross-ventilation. When matched with a dry climate, an air cooler is a highly efficient financial asset, but it is entirely at the mercy of the outside weather. Air conditioners bypass local weather conditions entirely by utilizing active refrigeration. They rely on a high-draw compressor system to pull indoor air over cold evaporator coils, actively extracting both heat and moisture from the room before pumping it outside. Unlike a cooler that depends on dry outdoor air, an AC system grants the user complete autonomous control over the indoor temperature and humidity. That level of control requires a heavy financial commitment. You face the highest initial purchase price at the store, followed by a severe, continuous monthly electricity bill. The building itself must also comply. An air conditioner demands a completely sealed room to function properly, halting all natural fresh air exchange. While variable speed inverter models can reduce the energy waste associated with the compressor cycling on and off, the baseline power draw required to refrigerate a room remains substantial. An air conditioner guarantees absolute indoor comfort, provided you accept the highest financial liability and adapt your home's structure to contain the cold. The home's exterior envelope acts as a massive thermal battery, continuously absorbing and trapping solar radiation throughout the day. Intercepting that heat before it enters the living space requires architectural defenses like external window shading, proper directional orientation, and strategic cross-ventilation. Once inside, the interior volume of a room establishes the baseline workload. High ceilings and open floor plans dictate exactly how hard any appliance must work to achieve a comfortable temperature. This quadrant chart maps installation effort against long-term cooling impact. Upgrading appliances is low effort, but architectural interventions like adding insulation sit in the high-effort, high-impact quadrant. By installing proper roof insulation, the home's cooling load drops significantly, achieving a cooler interior without electricity. Attempting to solve the heat problem by placing an oversized air conditioner in a poorly insulated house leads to compressor short cycling, excessive energy bills, and a failure to adequately dehumidify the air. Addressing the building's own greenhouse effect is a far more strategic, permanent investment than forcing a massive appliance to fight the physics of your house indefinitely. With the engineering mechanics clear, we can build a practical roadmap for making a purchase today. This flowchart breaks down the decision. Node 1. Is your climate consistently humid? The yes path eliminates the air cooler, leaving a choice between a fan or AC. For absolute temperature control in sealed rooms, the path leads to the air conditioner. This is the reality for humid coastal environments, where dehumidification is mandatory, and you are prepared to accept the higher electrical tariffs. If your local climate is hot but dry, and your home allows for excellent cross-ventilation, the logic points in a completely different direction. Here, an evaporative air cooler provides intense cooling power and massive electricity savings, provided you stay on top of the regular water maintenance. And for transitionary spaces, mild weather periods, or tightly constrained budgets, a properly placed fan remains a highly effective tool for physical comfort. The most effective cooling strategy relies on equipment that operates in sync with local climate physics.